Hello everybody, this is the second part of the lecture of aircraft equations of motion. In the first part, we have reached to 6 coupled nonlinear differential equations. The first 3 of them were the equations of linear momentum or conservation of linear momentum, and the second set, which were also 3 equations which represents the conservation of angular momentum, and we have stopped at this point. Let's complete our division of aircraft equations of motion in this lecture, starting with the Euler angles. Because in the last lecture, we have discovered that we have the gravitational forces which was represented in the inertial fixed system, which is the Earth's axis, and we want them to be in the body axis system to be integrated with the other forces, the propulsive and thrust forces, which were represented in the body axis system. Any attitude in general in the three-dimensional Cartesian space could be represented at most by 3 successive rotations. This is Euler hypothesis. The most famous transformation is yaw pitch roll transformation or ZYX transformation, which starts with the rotation about the z-axis with the yaw angle psi. Then a rotation about y-axis with a pitch angle theta, and finally with a rotation about x-axis with a roll angle phi. The accepted limits on the Euler angles are as follows. Theta ranges between 0 and 360 degrees. This is psi not theta, sorry. Theta ranges between minus 90 degree and positive 90 degree. This is the pitching angle. And the roll angle phi ranges between negative 180 degree and positive 180 degree. If the sequence is performed in different order than psi, theta, and phi, the final result will be incorrect. Psi, theta, and phi are called Euler angles. In flight mechanics, the Euler angles are used to rotate the Earth axis system into coincidence with the body axis system. The following illustrates the transformation of a vector Fe in the Earth axis system into the body axis system. So Fe equal Xe, Ye, Ze in the Earth axis system. So I hat E, J hat E, and K hat E are the unit vectors in the Earth axis system. If we rotate through the U angle theta about the Z Earth axis, K hat, which is perpendicular to the screen, we end up in some intermediate axis system I dash hat and J dash hat and K dash hat, which will be coincident with K hat. So the new vector will be in the new domain x dash, y dash, z dash, and it has components of x dash, y dash, and z dash. If we look at x dash from the transformation, x dash is the projection on I hat dash. So it will be equal to xe cosine psi, this component, plus ye sine psi. If we look at y dash, which is the projection on the j hat dash, it will equal to ye cosine psi minus xe sine psi. And z dash will be the same as zf. Or in the matrix form, it can be written as follows. This is the vector of x dash, y dash, z dash in the new axis system, and this is the transformation matrix. We got it from these equations, and this is the original components in the Earth's axis system. So we will call this matrix the rotation matrix about the third axis with a psi angle. It means that the intermediate vector f dash equals the rotation matrix R, which is function of the U angle psi, times the old vector f earth, which was represented in the initial Earth axis system. So f dash equal R3 of psi, which is function in psi, times fe. We will now rotate the intermediate vector f dash through some pitch angle theta about the y dash axis to some other intermediate axis system I double dash, k double dash, and j double dash, which will be perpendicular to the screen. It will be inside the screen to follow the right hand rule. So the transformation matrix will be as follows. This is the original vector in the first intermediate axis system, and this is the second rotation matrix, which is R2, which is the function of theta. This is a rotation about the y dash axis, and the resulting vector will be x double dash, y double dash, and z double dash. So f double dash equal R2 times f dash. But from the previous slide, we know that f dash was equal to R3 of psi, the third rotation matrix, which is function in psi. This rotation was around the z-axis times the vector in the Earth axis system, f Earth. Finally, we will rotate the vector f double dash through some roll angle phi about the x double dash axis, which is perpendicular to the screen, also inside the screen. I and j and k, this is j and this is k, and I is inside the screen, will be the body axis system. So the transformation matrix will be, this is the second intermediate coordinates of the f vector, x double dash, y double dash, z double dash. This is the first rotation matrix, which is R1 because it is a rotation about the x double dash axis with a rotation function or roll angle phi. So the resultant vector will be x body, y body, and z body, components of the F vector. So the F vector in the body axis system equals R1 times F double dash. But from the previous step, F double dash was equal to R2 times R3 times FE. So we substitute with F double dash from this equation. This is R2, R3, F in the original axis system, which is the Earth axis system. This is the original components, and this is the way how we transform a vector in the Earth axis system into the body axis system. Therefore, any vector in the Earth axis system can be transformed into the body axis system using the following transformation. F body equal R1 times R2 times R3 times the original components in the Earth axis system. The previous transformation is very useful in transforming the weight vector of an aircraft expressed in the Earth axis into the body axis system. So, the gravity vector referred to the body axis system can be obtained by transforming the gravity vector referred to the Earth axis system as follows. This is R1, which is function of roll angle phi, times R2, which is function of pitch angle theta, times R3, which is function of yaw angle psi, times the gravity vector in Earth coordinate system to get it in body coordinate system. This yields the following weight vector in the body axis system as follows. In summary, the input to the gravity equations are the numerical values of Euler angles, theta, phi, psi. The outputs of the gravitational equations are the components of the gravity vector gx, gy, and gz along the body axis x body, y body, z body, to be fed to the translational equation of motion, the three translational equation of motions, as follows. This is gx, this is gy, and this is gz. All the gravity components can be written as mgx, mgy, mgz, as shown in these three equations. Note that the first rotation by R3 with an angle psi results in the same vector as the original gravity vector, was coinciding with the rotation vector z earth. So the effective rotations was the second and third rotations only by pitch theta angle and roll phi angle respectively. That's why we don't see a psi angle in the final gravity vector after transformation into body axis. In going from the body axis system to the Earth axis system, we go through minus phi rotation, then minus theta rotation, then minus psi rotation. For these orthonormal transformation matrices, note that R1 with the theta minus phi equal R1 transpose with the same theta phi. R2 with minus theta equal R2 transpose. R3 with minus psi equal R3 transpose with the same psi. Note also that the rotation matrix is an orthogonal matrix, hence the inverse equals the transpose. Then F in the Earth axis system equal R3 transpose times R2 transpose times R1 transpose times the F vector in the body axis system. This is very convenient for transforming the acceleration or velocity vector in the body axis system into a vector in the Earth axis system. The use of the Euler angles psi, theta, and phi for expressing the orientation of the body frame x body, y body, z body with respect to the Earth-based inertial frame x Earth, y Earth, z Earth is critical for navigational purposes. This is the flight path equation. Make use of this transformation. We transform u, v, and w in the body axis system into dx by dt or x dot, y dot, z dot in the Earth axis system by these equations. This is the flight path equations. The input for these flight path equations are the Euler angles. Okay, this C for cosine and this S for sine. This is the abbreviation of cosine and sine. So the input for these flight path equations are the Euler angles along with the components of the linear velocity u, v, w with respect to the body frame x body, y body, z body. The solution of the flight path equations provide the complete 3D trajectory of the motion of the aircraft with respect to the Earth-based frame x Earth, y Earth, z Earth. Recall that u, v, and w are provided by the solution of the combined conservation of linear momentum equations and conservation of angular momentum equations. The six coupled differential equations, and they were nonlinear also. The question now is how to get Euler angles, how to get phi, psi, and theta angles, how to get them. The Euler angles will be derived from the components of the angular velocity in the body axis, which were p, q, r, through the solution of another set of equations, the so-called kinematic equations, which will be discussed next. First, let's consider the axis system x1, y1, z1 is parallel to the Earth axis system x Earth, y Earth, z Earth, but fixed at the aircraft CG. We can notice from the previous analysis that the angular velocity vector is given by omega equal psi dot plus theta dot plus phi dot. This is the yaw, or the time rate of change of yaw angle, time rate of change of pitching angle, and this is the time rate of change of the rolling angle. However, by definition, we also have that omega as a vector equal P, Q, R in the body axis system with unit vectors I, J, and K. So this is the angular velocities in the body axis system. So we can equate the right hand side of both equations to get the following: that omega equal bi plus qj plus rk, and this is equal to psi dot plus theta dot plus phi dot. The purpose of the kinematic equations is to derive an expression for the Euler angles in terms of the components of the aircraft angular velocities p, q, and r, starting from the transformation x1, y1, and z1 to x2, y2, z2 with a psi angle, and we have z1 equal z2. Hence, psi dot equal psi dot k1, which is perpendicular to the screen inside the screen. Okay? But k1 equal k2 because the rotation is around z. So k1 equal k2. Similarly, in the transformation x2 and z2 and y2, which is inside the screen, to x3 and y3 and z3 with an angle theta, and we have y2 equal y3. Hence, theta dot equal theta dot j2, which is equal to j3. Similarly, in the transformation from x3, y3, z3, and z3 and x3 is outward, out of the screen with an angle phi, and x3 equal the x body. This is the body, x is x, so x3 equal x body. Hence, phi dot equal phi dot I3, which is equal to I, which is the unit vector in the direction of the x body axis. Summarizing, we get that omega as a vector equal psi dot plus theta dot plus phi dot equal b I plus q j plus rk ijk of the body axis system. So this will be equal to psi dot k2 from this equation plus theta dot j3 from this equation plus phi dot I is the body axis unit vector. So now we will make some mathematical manipulation to get K2 and J3 in terms of I, J, and K of the body system. Now the objective is to derive an expression for K2 and J3 in terms of I, J, K of the body axis system. The rotation matrix R2 is used to correlate I2 J2 K2 with I3 J3 K3. So this is the rotation matrix R2. The rotation matrix R1 is used to correlate I3 J3 K3 to I J K of the body axis. So this is R1. This is not R1, this is R1 transpose. This is the inverse of R1, and this is the inverse of R2. From the third row, from this third row, we can get K2 equal minus sine theta times I3 plus cosine theta times K3. From the third row of the second matrix equation, we can get K3 equal sine theta times J plus sine phi times J plus cosine phi times K. Substituting back in the K2 equation with this K3, so now K2 equal minus sine theta I plus cosine theta, and K3 is substituted from this equation, so this is sine phi J plus cosine phi K. Rearranging, we get K2 in terms of I, J, and K. These are the unit vectors of the body axis, X body, Y body, Z body. So this is the K3, and this is sine theta, this is cosine theta from this expression, and K3 is brought from this expression. Again, from the second equation of the first matrix equation, we can know that J3 equal cosine phi J minus sine phi K. This is J3. From this equation, J3 equal cosine phi I minus cosine phi J minus sine phi K. This is J3 of this equation. So back to the original equation. So omega equal Bi plus Qj plus Rk equal psi dot plus theta dot plus phi dot. Psi dot, we proved that is equal psi dot K2, and now we have K2 in terms of I, J, and K plus theta dot J3, and now we have J3 in terms of J and K plus phi dot I. So substituting from these equations into the omega equation, we get the following expression. Now we have represented omega in terms of psi and theta and phi in the coordinate of the body axis system I, J, and K. By grouping the coefficients of I, J, and K, we get the following equations, which can be represented in the matrix form as follows. The inverse of this matrix can give us the kinematic equations as follows. These are the kinematic equations. It should be pointed out that the previous equations have a singularity associated with the condition of theta equal 90 degrees. This is one of the reasons why an alternative approach based on the use of quaternion is used for large-scale simulations. In summary, the input to the kinematic equations are the components of the angular velocities B, Q, and R. The solution of the kinematic equations provide the numerical values of the Euler angles psi, theta, and phi. Looking to the whole picture, given the forces and moments applied to the airplane, then using the conservation of linear momentum equations and conservation of angular momentum equations together to get the velocity and the angular velocity components, but the gravitational forces need the Euler angles to be computed in body axes, and the Euler angles themselves can be obtained from the angular velocity from the kinematic equations. So these are the kinematic equations. We have to solve them first to get the Euler angles to be fed to the gravitational equations to compute Gx, Gy, Gz to be fed to the conservation of linear momentum equations, okay, to solve them together with the conservation of angular momentum equations to get u, v, and w, p, q, and r, the velocities and the angular velocities in the body axis system. So, besides the Euler angles and the linear velocity components are used in the flight path equations. So the flight path equations, they need the Euler angles and they need the components of velocities, translational velocities, u, v, and w to get the airplane trajectory x, y, and z in the fixed inertial axis. So first you can get x dot, y dot, z dot, and by integrating these components you can get the position of the airplane with respect to the fixed inertial axis or the earth axis system.